In this slide, we are going to talk about introduction of the card movie, the objectives, movie cutscene, explanation of the concept, calculation, and the conclusion. So the team member is the team leader Rifdi Rawi, Taufik Shawaluddin, Irfan Zakwan, Nanzi Sheng, and Mia Arina.
For introduction, movies often feature high-speed chases and stunts that seem to defy the laws of physics. In this assignment, we analyze a scene from Too Fast, Too Furious, specifically the bridge race scene, to explore how real-world physics applies to cinematic action. For the objectives, firstly, to identify and analyze the physics principles involved in the bridge jump scene. Secondly, to apply Newton's laws of motion to explain the car's movement before, during, and after the jump. And lastly, to explore the role of forces, velocity, acceleration, and projectile motion in the stunt.
The physics concept applied to the scene is the projectile motion. What is projectile motion? Projectile motion is how things move when you throw them. Like when you throw a ball, it goes up, moves forward, and then comes down in a curved path because of gravity. When a car drives off the bridge, it moves forward while also falling due to gravity, creating a curved path. Whether it lands safely depends on its speed, angle, and height. If it is too slow, it won't make it across. In real life, air and friction can change the motion, so careful calculations are needed for safe jumps. For the parameters used to calculate the angle, we use the ux equal to u cos theta and uy equal to u sin theta, while to calculate the displacement, we use the formula sx equal to uxt and sy equal to uyt plus 1 over 2 gt square, where the u is the initial velocity, s is displacement, t is times, and g is gravitational acceleration.
As for my parts, I'm going to present some of the calculations of our assignment. Based on the clip, we could conclude that the initial velocity of the R34 is 160 km per hour, and we also assume that the bridge is about 35-degree incline. First and foremost, we convert the initial velocity into SI units, which is meter per second. After that, we resolve it into two components, which is the S component and Y component. And we're using trigonometry to look for their values. From the Y component, we could calculate the time taken for it to reach the ground again by using the formula S equal to ut plus 102 at squared and substituting Sy equal to 0. Thus, the time taken is about 5.198 seconds. And with this time, we are able to calculate the horizontal distance traveled by the car by using the same value, but with this time we substitute Ax, which is equal to 0, since we ignore the air resistance. So as conclusions, the bridge is about 189.21 meter long.
So, moving on to the next calculation. What happens if the car don't have enough initial velocity? Let's just assume that the car travels at a speed of 100 km per hour, which is equivalent to 27.78 meter per second, with a launch angle of 35 degrees. From this velocity, we can break it down into horizontal and vertical component. For horizontal, we get 22.76 meter per second, and for vertical component, we get 15.93 meter per second. For horizontal motion, we use kinematic equation to determine how long the car stays in the air before hitting the ground again. Using the equation Sy equal to uyt plus ayt square, where Sy equal to 0 and ay equal to gravitational acceleration, solving for t, we get that the car stays in the air about 3.248 seconds. Now, using the time in the air that we found, we can calculate the distance of how far the car travels horizontally, which is about 73.99 meter. Finally, we can compare this value to the calculated value earlier, and we found that the distance traveled by the car horizontally is lesser than the gap of the blades. To conclude, the car didn't make the jump and fell into the river.
In conclusion, cars stunts defy gravity, but in reality, every jump follows projectile motion controlled by speed, angle, and gravity, which is 9.81 meter per second squared. A real car would follow a parabolic path, slow mid-air, and crash hard. Hollywood, however, bends physics. Car fly further, stay aboard longer, and land smoothly for maximum thrill. While real-world physics could make these stunts impossible, the franchise blends just enough realism with movie magic to keep the action exciting.